All right. Hello, hello, everybody. Welcome back again. Today is the day. This is it. We are finally going to talk about the trigonometric functions. I'm super excited because this stuff is just so fun. Trigonometry is just such a robust field and just such a cool subject. I'm really excited to get started. So let's just get started. Here we go. All right. Slides. So this is section 6.3, and this is all about the trigonometric functions. So here's the overview. We're going to recall the unit circle. Okay, the unit circle, which we talked about back in 6.1 and also earlier in the course. Then we're going to develop trigonometry. It all boils down to this unit circle picture. Then we're going to get what I like to call the big picture. This picture is like the thing that you're going to fall back on anytime you want to think about trigonometry or evaluate a trigonometric function. It's going to go back to this big picture. Then we're going to define all six of the trigonometric functions. And then we're going to spend a significant amount of time evaluating the trigonometric functions at those standard angles. Hopefully by now you are working on memorizing some of those standard angles, the ones you were supposed to memorize. Then I'm going to give you another thing, a couple things to memorize that are going to help you evaluate these functions, and that's going to be the special right triangles. You might have seen these in a previous class already. If you did, great. If not, you're going to get a chance to see them right now. But knowing those basic standard angles and knowing these special right triangles is going to allow you to evaluate all of the trigonometric function values that we're going to be concerned with. Then I'm going to finish up by giving some number theoretic results about the trig functions to kind of motivate why I am relying so heavily on these special right triangles, kind of motivating the reason for doing that and why we're allowed to do that. Okay, so let's quickly recall the unit circle. Hopefully you remember this very well at this point. A circle of radius 1 is called a unit circle, and when we center it at 0, this is often what we call the unit circle, just like that. It's got this equation, x squared plus y squared equals 1, and this picture here, this circle, I should say, is the foundation for all of trigonometry. This is where it's all going to come from, okay? All right, so how are we going to do this? Well, think about it like this. We're going to pick a point P, which is x comma y, on the unit circle. So in other words, whatever x and y are, they satisfy the equation x squared plus y squared equals 1. Could be any point, could be this point, could be this point, could be this point. We're just going to pick a point on the unit circle, okay? Now we're going to let theta be the angle between the positive x-axis and the ray that passes through the point x comma y. So for example, come back. There you go. So for example, if I pick maybe this point right here, there's a ray that goes from the origin that passes through that point. Okay, just like that. And we're going to say that this is the angle theta. That's the idea. Okay. Now, as theta changes, as that angle changes, the point that we just picked moves around the circle, and its location on that circle is directly dependent on theta. Maybe you can kind of picture it, right? So imagine this point here. As theta changes, that point is going to move around the circle. And the location of that point directly depends on what theta is, the measure of that angle theta, right? So in other words, we can parameterize the circle using the angle theta. That essentially just means we can describe the circle and the points on that circle using that angle theta. All right, so how do we do that? How do we actually describe the circle and the points on that circle just using the angle? Well, we're going to split things up into horizontal behavior and vertical behavior. So we're going to describe the vertical displacement of the point as a function of theta, and then we're going to describe the horizontal displacement of the point as another function of theta. So basically, we're going to say, hey, what's happening horizontally and what's happening vertically? And in doing so, we can parameterize the entire circle just depending on that angle theta. All right? And so this is the big picture, my friends. Boom. Okay. So when I talk about the big picture, this is the big picture I mean. This is the picture that is the foundation of all of trigonometry. This is how we are going to define the functions sine of theta and cosine of theta. They all boil down back to this big picture that you see right here. So I'm just going to leave it up on the screen for a minute, and I want you to just ponder it, just stare at it. Okay. Now, this is a great time to verbalize something, to say something out loud. Even better if you're watching this with a friend or something, just describe something you see on the picture out loud. Okay. Now, I'm going to talk a little bit more about this, and then we're going to more rigorously define what's going on here. So let me zoom in a little bit. There we go. So we have the unit circle, and we have this point x comma y on the unit circle. Here is the idea. The horizontal displacement of this point is given by the value x. All right. And that horizontal displacement, we're going to call it cosine of theta, right? Here's the angle theta. So cosine of theta is just this value right here. It's the x coordinate of this point. So quite literally, x equals cosine of theta. Literally. Now look at the vertical displacement. The vertical displacement of this point. This is what we define as sine of theta. Okay. Another note about notation here. This is one of those situations where cosine of theta is equal to cosine of theta. So understanding the function notation is going to be really important in this chapter. This is a situation where, because things can get really cluttered with what we're going to explore coming up here, we like to just omit the parentheses and write cosine of theta. But these are just functions, okay? These are really, 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 really special functions, cosine and sine. There's no multiplication going on here. This isn't cos times theta. These are just really special functions, so we gave them special names, cosine and sine, okay? This is like f. Think of it as f. That's what that is. This is f of theta, all right? But we remove the parentheses because things are going to get a little bit cluttered. Now, back to the big picture here. X is cosine theta, and y is sine theta. X is the horizontal displacement of this point, wherever that point is on the circle, and y is the vertical displacement of that point on the circle. That's sine of theta. Now, as this point moves around, these values are going to change, right? So as this point moves around, that means that theta is going to change, and that means the point, how high up it's going to be, is going to change. It's going to go up and down between -1 and 1, and it's going to go left and right between -1 and 1, and we are encoding those two different behaviors as cosine of theta and sine of theta. All right, that's the idea. We're going to see some really cool animations in the next section when we talk about the graphs of these functions. Oh, wait, I'm sorry, the section after that when we talk about the graphs. But this is the big picture. Okay, so this is the picture you want to have tattooed in your brain. Everything boils down to this big picture. Okay, now let's define these functions more specifically. There are 6 trigonometric functions, and they all start with sine and cosine. So the sine function is defined as sine of theta equals y, and it's giving the y coordinate of a point P on the unit circle. Equivalently, the sine function is giving you the vertical displacement of that point P, okay? Now, remember, theta is an angle, and it can be any real number, like we talked about in the previous section, right? The angle can be any real number, and so that means that the domain of the sine function is all real numbers. The sine function can take in any real number, and it will tell you the vertical displacement of that point, whatever that angle is, right? Now, the vertical displacement, if you remember the big picture, it can be any value between -1 and 1. So again, the vertical displacement can go all the way up to 1 or all the way down to -1. So that means that the range of the sine function is -1 to 1 inclusive, right? It could be equal to -1, it could be equal to 1. Now, this is an important result. This is one of the reasons we love the sine function. The sine function is bounded, meaning whatever sine of theta is, that output, it's got to be between -1 and 1. So sine of theta doesn't go very far in terms of outputs. It sticks between -1 and 1, and it can be any number in between -1 and 1 also. Could be 0, could be 1/2, could be 1/7, could be 0.9999998, could be any number between -1 and 1, okay? That's it. Now, on the other side of things, there is the cosine function. The cosine function is defined as the x coordinate of that point on the circle, that point P. And the cosine function is giving us the horizontal displacement of that point P, back and forth, right? Now, again, theta can be any real number, so the domain of the cosine function is all real numbers. And just like before, the horizontal displacement can be any value between -1 and 1. So the range of the cosine function is -1 to 1. So, meaning whatever this horizontal behavior is, it could be as big as 1, or it could be as low as -1, right? And it can go anywhere in between, back and forth, back and forth. So the range of the cosine function is -1 to 1, and the range of the sine function is -1 to 1. Also, we love, love, love cosine as well, because that means cosine is bounded. It's a bounded function between -1 and 1. Okay, now we've got sine, we've got cosine. The other four trigonometric functions are just modifications of these two functions, all right? The next one we're going to talk about is what's called the tangent function, tangent. So the tangent function is defined as the ratio of sine and cosine. In particular, it's sine of theta over cosine theta. And there's some really cute results that follow from this definition. Essentially, what we're taking is we're taking the vertical displacement and dividing it by the horizontal displacement. You could even think of it as we're taking the rise and dividing it by the run. Does that sound familiar? Hmm. Rise over run. Where have we heard that before, I wonder? Oh, that's right. That's the slope, right? That's the slope formula. So the tangent function is actually giving you the slope of the line that passes through the origin and the point P. And literally, that's what it is. It is the slope of that line. It's sine of theta over cosine theta, which is, again, the rise of L and the run of L, and that's the slope of L. So if we go back to the big picture here, let me erase, delete. We have this. Uh, there's this line right here, right? This line. I could do better than that. You know what? I'm just gonna, here. There's a line, pretend that's a straight line, and the slope of this line is literally equal to y over x, right? If this point is y over x, well, the slope is going to be the rise over the run. But remember, y is sine of theta, and x is cosine theta. So the slope of that line is the tangent of theta. That's how we define it, all right? So whenever you think of tangent of theta, think of the slope of that line. That's it. That's going to help out a lot. Okay, now some details about this one. The domain is a little bit different. Okay, the domain is a little bit different in this case because cosine of theta could be 0. The horizontal displacement could be 0, and because we have a ratio here, we have to exclude all of the points where cosine of theta is equal to 0, right? So the domain of tangent is not the real numbers. There are some exclusions. We need to cut some points out of the real numbers. So the domain of tangent is all real numbers such that cosine of theta is not 0, okay? More specifically, it's all the real numbers where theta is not an odd multiple of pi over 2. Okay, let me explain this a little more in a second here. Remember 2k plus 1, that describes any odd number. Even numbers can be written as 2k. Odd numbers can be written as 2k plus 1. We kind of saw that back in chapter 5 when we were looking at sequences, for example. So the domain of the sine function excludes all multiples of pi over 2. And now let's make sense of why that's the case. Why are we cutting out all the odd multiples of pi over 2? What are we going to do? Go back to the big picture. Everything boils down to this big picture. Let me delete this for a second. Okay, now remember the, hey, come here, there we go. The tangent of theta is the slope of this line, right? Well, what happens when theta is pi over 2? Well, what is the angle pi over 2? Do you remember it? Can you picture it? Okay, pi over 2 is this angle right here. Ooh, I can do better than that. That angle right there. So when theta is pi over 2, the point is going to be right here. And so the line that we're looking at is vertical. And what do we know about the slope of a vertical line? It's undefined, right? Has no slope in that sense, right? So that is why we are omitting those angles from the domain of tangent, because as this line rotates, eventually it'll become vertical. And when it's vertical, the slope is undefined, right? So that happens when we are at pi over 2. It also happens when we are at 3 pi over 2 or 3 halves pi, right? It also happens when we go back around up here. That'd be 5 pi over 2. It happens when we go around here again. That'll be 7 pi over 2. So we're talking about 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, odd multiples of pi over 2. So those are cut out of the domain of the tangent function, all right? And that's what this gobbledygook here is saying. No straight, no vertical lines. um, Now, on the other side of things, the slope of a line could be any real number, right? The slope could be 0, the slope could be negative, the slope could be positive. It could be any real number. So the range of the tangent function is all real numbers. This is a little bit different, right? The tangent function is not bounded. The output of the tangent function can be any real number. All right. So it's a little bit different. Okay. Now, the remaining three functions are actually pretty simply related to these first three functions. They're just the reciprocals of these functions. So we're going to take each one of the three functions we just learned about and we're going to reciprocate. And that's going to give us our other three trigonometric functions. Here we go. So what is the cosecant function? The cosecant function is 1 over sine of theta. That's it. So we're taking sine of theta and we're reciprocating it, and we call that result the cosecant function. It's 1 over y. Just like we saw a moment ago, we have to be careful about division by 0 because sine of theta could be 0. The vertical displacement of that point could be nothing. It could be 0, right? So we need to exclude those points from the domain of cosecant. So the domain of cosecant is all real numbers where sine of theta is not 0. Okay, so when is the vertical displacement equal to 0? Well, go back to that big picture. It's going to come back. I'm going to sound like a broken record very quickly here. When is the vertical displacement equal to 0? Right when we're facing like this way, right? So it's at angle 0, it's at angle pi, it's at angle, oops, sorry, it's at angle 2 pi, it's at angle 3 pi, it's at angle 4 pi. And what's happening is we're getting a 0 vertical displacement at every integer multiple of pi, right? Every integer multiple of pi. So if we check this out, we're cutting out all of the integer multiples of pi. That includes 0, 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. All those times pi, we got to cut those out of the domain of the cosecant function. Again, you do not need to memorize this stuff. I don't recommend memorizing all this stuff. What I recommend is making sense of what sine and cosine are, and then remembering that this is just the reciprocal of sine. That's it. So if you can understand sine, you can understand cosecant. It's just its reciprocal. And there's some other cool results too. We're gonna build on this over the next few sections. But the range of the cosecant function is this set. It's the interval from -infinity to -1, including -1, and then from 1 to infinity. And the reason for that is, I think, is actually kind of cute. It's something that we saw back in chapter 1 when I was talking about it was 1.6 actually. It was 1.6 where you can reciprocate fractions. You can reciprocate fractions and that changes the inequality, right? Changes the direction of it. If you don't remember, go look back in section 1.6. But remember, the size of sine of theta is less than or equal to 1. It's bounded, right? So if we reciprocate that, that means that 1 over sine of theta in size is greater than or equal to 1. But this is the size of cosecant. So that means the output of the cosecant function has to be greater than 1 in size. So that means it's got to be here or it's got to be here. That's the range of the cosecant function. Cool stuff. All this stuff just comes together. That's one of the reasons I love trigonometry. All the puzzle pieces just fit together in really beautiful ways. All right. Next function is the secant function. So the secant function is the reciprocal of cosine. So again, we're just taking cosine and reciprocating it. That's all it is. 1 over cosine, 1 over x. The domain, same kind of considerations, right? We need to make sure we're not dividing by 0. So the domain of secant is everywhere that cosine is not 0. All right. Well, when is cosine equal to 0? When is the horizontal displacement equal to 0? Go back to that big picture. Here we go. Here we go again. When is the horizontal displacement equal to 0? When we're about here. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Wait a minute, this sounds familiar. These are all the odd multiples of pi over 2. And guess what? Those are exactly the numbers that we have to cut out of the domain of secant. Odd multiples of pi over 2. Again, you don't memorize this. Just go back to that big picture and make sense of what cosine and sine are, and you will be set, okay? Same as before, cosine is bounded, and we love that. We love that about cosine, but that means its reciprocal is unbounded. Its reciprocal is unbounded. So the range of the secant function is 1 to infinity and negative infinity to negative 1, including those endpoints, negative 1 and 1. Okay. One more function. You can probably guess what it is. It's called cotangent, and it's just the reciprocal of tangent. So cotangent is the reciprocal of tangent. We're just taking the reciprocal of tangent, which is sine over cosine, and we're going to reciprocate that to get cosine over sine. Um, just like before, we need to be wary of division by 0. So the domain of this function is everywhere sine is not 0. When is sine of theta equal to 0? I'm not going to go back this time. We have to cut out all of the integer multiples of pi. So the domain of cotangent is everything except integer multiples of pi. Okay? Now the range, so again, this is what's interesting. The range is all real numbers again, because the reciprocal of any non-zero slope is still a real number, right? Still a real number. Note that theta can't be 0. Theta is not equal to 0, right? So that means any slope of a line, we can reciprocate it, and or as long as it's not vertical, right? And we'll be okay. So the range of cotangent is also all real numbers. Okay, now summarizing everything, this is, I wouldn't say the big picture, this is everything written in one big block. Sine of theta is vertical displacement, cosine theta is horizontal displacement, tangent theta is the slope of that line, and then these are just the reciprocals. That's it. So you do need to memorize all of these functions and be able to picture sine, cosine, and tangent on the unit circle. But again, it just goes back to that big picture. So if you ever forget, draw that picture. I'll flash back one more time. We're gonna see this so many times. This is where it all comes from. You don't need to memorize a ton of stuff. You just need to remember this picture and that x is cosine, which is horizontal displacement, and y is sine, which is vertical displacement. And that will carry you way farther than you could ever imagine. Um, Now, one thing you might have noticed, the names of these functions are kind of related. There's like sine, cosine, secant, cosecant, tangent, cotangent. There's a reason for that. That's not a coincidence. The co part of these names comes from the fact that the co-related functions are co-functions of each other. We're going to talk about that in the next section, but basically they give the same value at complementary angles. Don't worry about it yet. We'll talk about that in more detail in the next section when we talk about right triangle trigonometry, okay? But there's a reason they're called co-functions. All right, now let's do some examples. So, well, I'll say this before we get to this example. Anytime, anytime you are being asked to evaluate a trigonometric function, you need to picture the unit circle. So you'll hear me say that a lot. Imagine the unit circle, draw the unit circle, picture the unit circle, and that is going to give you the answers when you have that picture. So consider this one. Let P be the point negative 1/2, comma, root 3 over 2, be a point on the unit circle. Find the values of all 6 trigonometric functions. Okay? All 6 of them. Now, I do want you to try this on your own, so think about it for a minute first. All right. Now, verbalize something that you think might help you take the first step in doing this problem. Maybe something that you could do. All right. Now try to work it out on your own. You know what my tip is going to be probably. Uh, Imagine the unit circle, sketch the unit circle, plot that point, and that will be the best guide you could ever ask for to answer the rest of these questions, to evaluate those functions. Go for it. All right. Now let's do it together. So here, I'm going to draw the unit circle. Picture the unit circle. So where is that point? Okay, well, here's the unit circle. X, Y. X is negative a half. Y is root 3 over 2. So that point is over here. Okay. In fact, we might not even need the unit circle picture for this, but this is the point negative 1/2 root 3 over 2. Okay. Now, remember, what is cosine? Cosine of theta is the horizontal displacement, right? It's X. But in this case, that's negative 1/2. What is sine of theta? Sine of theta is Y, and that's root 3 over 2. So we've already got two of them. And guess what? All the other ones are just dependent on cosine and sine. What is tangent? Tangent is sine over cosine, which is root 3 over 2 over 1/2. And when we simplify that, we're going to get what? Flip, multiply, we get root 3. Okay, now let me highlight these for a second. We've got cosine, we've got sine, and we've got tangent. If we want to get secant, cosecant, and cotangent, you just take those results and reciprocate, and you're done. That's it. That's how quick and easy it can be. All right, what do I got here? So, oh, there it is. It's all just written on one slide. That's it. Um, Here's sine, here's cosine, here's tangent. Oh, Sue, I messed that up. Let me go back. This should be negative. My apologies. Negative. So that's negative. I forgot that. There we go. There you go. So that's negative root 3. Um, then we reciprocate. What is cosecant? We reciprocate sine. What is secant? We reciprocate cosine. What is cotangent? We reciprocate tangent. And that's it. That is it. All right. Okay. Next example. We're going to do a lot of examples in this section. Let me be sure. Yeah, yeah. Okay. So try this one. Try to evaluate the six trigonometric functions at these quadrantal angles: 0, pi over 2, pi, and 3 pi over 2, or 3 halves pi. I'll say this. This might seem like a lot of work, but just remember what sine and cosine are and try to picture what these angles are, okay? So try at least a couple of these on your own, maybe just the first two. Think about it. Okay, verbalize something, say out loud, maybe which angles you want to try out. Okay, now work out the ones you decided to pick, and then we'll do all of them together in a minute. Okay, here we go. All right. So first thing we should kind of well, remember the big picture. Everything boils down to the big picture. Remember what sine and cosine are. And then it helps to refresh your memory of what those angles look like. Remember, these are actually all angles that you were supposed to memorize, except for this one, right? Which is just 1.5 pies. But all you need to do is think about what these angles look like. Imagine where the point is going to be. Remember that x is cosine, y is sine, and then everything falls out from that. So here we go, one at a time. So um, here, the angle here is 0. So we're looking at this angle right here. This is the point 1 comma 0. And from that, everything's going to fall out, right? Sine is 0. Oh, I actually did it piece by piece. Okay. Let me see. Well, Mm, okay, I could have better organized this, but I'll do it this way. For this point, sine of 0 is 0, cosine of 0 is 1, and then tangent of 0 is going to be 0. The slope of that line is 0. Um, then coming back this way, cosecant is 1 over sine, right? But remember, I'm sorry, sine was 0, So cosecant is actually undefined here. Yeah, cosecant is undefined here. Secant is 1 over cosine, so we're going to get 1 over 1, which is 1. And that's basically it. Now, I'm going to follow my slides a little more here so it doesn't get too confusing. But for each one of these points, we're just going to go through and evaluate sine. All right, so sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 halves pi is -1, right? The vertical displacement in that case is going to be -1. Okay, cosine of 0 is 1. Cosine of pi over 2 is 0. There's no horizontal displacement. Cosine of pi is -1, right? Because we're all the way out here at -1. Cosine of 3 halves pi is 0, because now we're going all the way down to here. No horizontal displacement at that point. All right, moving along. Tangent is just sine over cosine. It's the slope of those lines. So maybe if I do this, here, I'll do this. Draw this real quick. Okay, so when the angle is this, the slope of that line is 0. When the angle is this, right, we're pointing up, that's a vertical line, so the slope is undefined. When the angle is pi over here, the slope of that line is 0 again. When the angle is 3 pi over 2, this is what it's looking like. It's pointing down, right? So that's going to be undefined again because it's a vertical line. And that's how it goes. So those are sine, cosine, tangent. For cosecant, again, we're just reciprocating what we already know about sine. So sine of 0 is 0. 1 over 0 is undefined. Sine of pi, imagine the unit circle, is 0. 1 over 0 is undefined. Let's see, a sine of pi over 2. Imagine the unit circle. That's 1. 1 over 1 is 1. See, sine of 3 pi over 2. Imagine the unit circle pointing down here. That's -1. So 1 over -1 is -1. So what I'm doing with every single one of these is I'm just imagining the unit circle, drawing a little sketch, asking, where the arrow would be pointing, asking what's the vertical displacement versus the horizontal displacement. That's it. That's it. All right, secant. Okay, again, cosine of 0. Okay, here's the unit circle. 0 looks like this. That's 1. Cosine is 1. Horizontal displacement is 1. 1 over 1 is 1. Okay, what is pi? Pi is over here, so it looks like that. Cosine is -1. 1 over -1 is -1. There we go. Um, 1 over 0, cosine of pi over 2. Okay, where's pi over 2? It looks like this. 0 horizontal displacement, so 1 over 0 is undefined. 3 pi over 2, it looks like this. Again, 0 horizontal displacement, 1 over 0, it's undefined, and so on. They all just fall out. They all just fall out. Okay. Same with cotangent, and I'm just going to blow through these ones because it's really just the same idea. Cotangent pi, we already evaluated it. It's undefined because we're dividing by 0. Cotangent pi over 2 is just the reciprocal of what we got for tangent of pi over 2. It's going to be 0. Well, I guess I should say it's cosine pi over 2 over sine pi over 2, which is 0 over 1, which is 0. Cosine 3 pi over 2 over sine 3 pi over 2 is 0 over -1, which is 0, and on and on and on. It just comes out so quickly at that point. All right, another example. So for this one, I think, okay, for this one, I will do the first part and explain how I do it. And then I would like you to try the second part, the cosine of -450 degrees. Remember, angles can be measured in radians or degrees. It doesn't matter. They're just an angle measurement, and we are evaluating a function at an angle, okay? So the output does not matter because these functions are well, I'm sorry, the unit that we are using for the input does not matter. These functions are well defined. So I'll do this one, and then you can do this one on your own. So we're going to find these exact values of sine of 3 pi. All right. So remember, as a point moves around a circle, right? Where's 3 pi? That's 2 pi. That's 3 pi, right? So we're facing that direction at the end. But as the point moves around the circle, its position repeats every 2 pi radians, right? If I like am here and then I go around a full revolution, I'm back here. and then I go around again, and I'm back here, and I go around again, and I'm back here. So it repeats every 2 pi radians. We can still evaluate the trig functions at angles that are larger than 2 pi. We just need to find the remaining fraction of a revolution after dividing the angle by 2 pi. This might sound complicated, but you've actually done it a handful of times already. In other words, we're going to repeatedly subtract multiples of 2 pi from the angle until we get an angle that's less than 2 pi. And then we're just going to evaluate the function at that remainder. All right. So, this might sound a little familiar. It's like we're throwing away the whole rotations and just taking a look at what remains, like the remainder of a rotation. This sounds very familiar. So technically, this is a form of what's called modular arithmetic. And what we're doing is sometimes mathematicians and engineers and physicists will say we're modding out by 2 pi. So in essence, what we're doing is we're dividing the angle by 2 pi and then keeping the remainder. So that's Euclid's division lemma. Whoa, it strikes again. Euclid's division lemma popping up over and over and over. Man, is there even a chapter where it doesn't pop up? I don't think so. I don't think so. Yep, 3, 4, 5, I think. Yeah, 5. Man, it's everywhere. It's everywhere. So let's see it in action right now. Okay, so 3 pi is equal to 2 pi plus pi. So what that means is that sine of 3 pi is going to be equal to sine of 2 pi plus pi, but this full rotation is not going to matter. It's not going to matter at all. So you can basically ignore it and just evaluate sine of pi. Vertical displacement there is 0, so sine of pi is 0, and that's it. So you can mod out by multiples of 2 pi. Yeah, the 2 pi term represents a full revolution. What this means geometrically is that the point on the circle here is going to be the same as for the angle pi. So you can mod out by 2 pi. Okay, now you try to do the second one. Okay, I'll give you give you a minute to do this. You try to evaluate cosine of negative 450 degrees, and yeah, think about it for a sec. Okay, now verbalize something. Maybe what could you mod out? All right. Now try to evaluate it on your own. Remember, you can mod out by something to make the evaluation straightforward. All right, now let's do that one together. So remember that 360 degrees is a full rotation. So we can mod out by 360. And then whatever is remaining, that's where we'll evaluate cosine. Okay, so negative 450 is the same as negative 360 minus 90. So really, cosine of negative 450 is the same as cosine of negative 90, which is going to be 0, right? Negative 90 is actually this angle right here. And so it's going to be the same as, well, the cosine value is going to be the same as negative 450, in this case, 0. Another little point I want to make before we get to the special right triangles. Remember that, let me highlight these, in fact. Negative 450 degrees is not equal to negative 90 degrees. Okay, those two angles are not equal. What is equal is the output of the cosine function at those angles. Okay, so be wary of that. It's a common mistake where people are just like, oh, negative 450, that's equal to negative 90 and yada yada yada. That's not true. Okay, negative 450 is not equal to negative 90. Even just saying it out loud, like 450 is equal to 90, that doesn't make any sense. What's different here is the output of the cosine function at negative 450 is equal to the output of the cosine function at negative 90. Inputs and outputs. That's why we were emphasizing them so much early on, right? The outputs of this function are the same at those two angles. That does not mean the two angles are the same, okay? So beware of that. Beware of that. Now, okay, so now we got to talk about some special right triangles because we're going to evaluate these functions at a whole bunch of different angles. If we want to evaluate them at the standard angles that I gave in the previous section, the outputs of these trig functions follow a pattern that's based on two special right triangles. You may have seen these before if you took geometry or algebra, but the two special right triangles that you're going to want to memorize are the 30-60-90 triangle and the 45-45-90 triangle. Okay. And again, these are what you're going to want to commit to memory. And once you have all that covered, everything is going to fall out. So you do need to memorize the lengths of the legs of these two right triangles that I'm going to show you in a minute. And if you do that, then you can immediately evaluate any trig function at the standard angles without computation. So like I mentioned in the previous lecture, don't try to memorize the whole unit circle. If you look it up online, you'll find a unit circle that's just packed with information. You don't need to memorize all that. Just get comfortable with the standard angles, memorize these two special right triangles, and you'll be set. Okay? Oh yeah, here you go. This is exactly what I just said. Yeah, there you go. So let's see the triangles. Here are the two triangles. So stare at them for a minute. Just gonna throw up the thinker. Stare at them, ponder them. Okay. All right. Now let's talk a little bit about them. So here is the 30, 60, 90 triangle. Okay. And this is what we need to know. The hypotenuse of this right triangle has length 1. And consequently, or I should say, as a consequence of these angles, this leg is going to have length root 3 over 2, and this leg is going to have length 1/2. Root 3 over 2 is the long leg, 1/2 is the short leg. Okay. So you'll see me when we're in class, like when we're evaluating these trig functions at these angles, I'll constantly be asking myself, like, you'll see my hand go like this because I'm wondering what is the short leg, what is the long leg? This is the short leg, this is the long leg. Now, in the 45-45-90 triangle, this is an isosceles triangle. So these two legs actually have the same length, and the length is root 2 over 2. So if you've got a 45-45-90 triangle, the two legs are the same, root 2 over 2 and root 2 over 2. These are the lengths that you need to memorize. 1/2, root 3 over 2, and root 2 over 2. Okay, that's what you need to commit to memory. And the reason for that is this bullet point right here. At the standard angles that we talked about in the previous lesson, the values, the outputs of sine and cosine are gonna be those numbers, either 0, 1/2, root 2 over 2, root 3 over 2, or 1, depending on what angle it is, and up to a sign change. So it might be negative 1/2, it might be negative root 3 over 2, it might be negative root 2 over 2, or negative 1, or something like that. But it's always going to be those numbers plus or minus every single time at all the standard angles. Okay, so that's why you commit these to memory. Just commit those to memory, and then these will be the lengths. These will be the sine and cosine values, plus or minus. Once you know sine and cosine, you get all the other trig functions for free. Tangent, cosecant, secant, all those things, cotangent. All right. Um, yeah, that's exactly what I just said. So yeah, all the others will be easily deduced from just knowing these triangles and those standard angles, okay? We're going to see several examples of that in a minute. So this is where I'll say, you might ask yourself, well, like, aren't there a lot more angles than just 30, 60, 90, and 45? The answer is yes. There are obviously infinitely many more angles than these. But it turns out that these exhaust all of the nice values of the trig functions. And I'll explain what I mean by nice when we get to the end of this section and look at some number theoretic results about the outputs of these trig functions. So what I'm saying is these values, including 0 and 1, those are all of the nice values. And we'll make more sense of that in a few minutes. Okay, so let's practice. Okay, this is where it gets fun. This is one of the things I love about trigonometry. As long as you are comfortable visualizing these standard angles and you have those two right triangles memorized, you'll be good to go. I'm going to do this one first, and then I'll let you do the next one. So we're going to find the exact values of cosine pi over 4 and sine of pi over 4. How do we do it? Imagine the unit circle. Imagine the unit circle, okay? So we're going to imagine the unit circle. We're going to imagine the angle pi over 4, which is right here, okay? And when we imagine that angle, it forms a right triangle with the x-axis, okay? And excuse me, pi over 4 is equal to 45 degrees. So what you're going to have is a 45, 45, 90 triangle, which means the lengths of the legs are root 2 over 2. Guess what? That's cosine and sine. We're done. That's it. That's it. Yeah, that's it. So um, cosine is horizontal displacement, so it's root 2 over 2. Sine is vertical displacement. It's also root 2 over 2. And we're done. That's all you need. Okay, now let's let you practice one. Little hint before you do this, remember the quadrant. You're still going to draw a right triangle. It will be one of those special right triangles, but just keep in mind the quadrants, okay? Keep in mind the quadrants and the sign, like the plus or minus of these values, okay? So think about this one for a minute. Find the exact values of cosine of 3/4 pi and sine of 3/4 pi. All right. Now, say something out loud, maybe what you will try first or what you remember the easiest, and go from there. Okay. Now work it out on your own. Draw a sketch. Remember the unit circle, sketch that angle, and then see which one of those special right triangles you've got. Okay, now let's do it together. Here we go. All right, sketch the angle. Oop, there it is. There it is. Okay. Sketch the angle out. Remember, 3 pi over 4 is 135 degrees. So when you draw the angle, it's going to be over there. It's still going to give you a special right triangle right here. Okay, just like that. But again, it's a multiple of 45 degrees. It's a multiple of pi over 4. So you're going to have a 45, 45, 90 triangle. The legs are going to be root 2 over 2. The only catch here is that this one is going to be negative because you're in the second quadrant, right? You're in the second quadrant, so the x coordinate is going to be a negative value right there. Now you can just read it off. Cosine of theta is horizontal displacement, which is negative root 2 over 2. Sine of theta is vertical displacement, which is going to be positive root 2 over 2. And that's it. There we go. Okay, let's do another one. How about this one? 27 pi over 4. That's the angle. We're going to evaluate both. I'll just go ahead and do this one. It's going to be about the same. The only thing you got to remember is modding out by 2 pi. Okay, so 27 pi over 4 is 6 3/4 pi. So we can basically toss out the 6 pi's and just draw the angle that's at 3/4 pi. Okay. That's actually just going to be the same picture that we see right here. That's 3/4 pi, right? So it's going to be the same results, right? That's going to be the same results. Cosine of 27 pi over 4 is negative root 2 over 2, horizontal displacement. Sine of 27 pi over 4 is root 2 over 2, vertical displacement, just like we saw right here. Horizontal displacement, cosine, vertical displacement, sine. That's all it takes. Okay, let's do, okay. Now let's do this one. I do want you to try this one on your own first, and then we'll do it together as well. So think about it for a minute. Right. Now say something out loud. Do you remember where that angle is? Okay, now work it out on your own, and we'll do it together in a moment. One thing I will say is ask yourself, what is the short leg and what is the long leg? There's my hint. Okay. All right, here we go. So pi over 6. So you want to remember where pi over 6 is. And in this case, because pi over 6 is equal to 30 degrees, we're going to have a 30, 60, 90 triangle as the triangle that's formed, right? So whenever you're working with multiples of pi over 6 and these 30, 60, 90 triangles, you really want to ask yourself, which is the short leg and which is the long leg? And that's why you'll see me do things like this, where I'm like, okay, wait, does the triangle look like that or does the triangle look like that? Because if it's that, then the long leg is down here and the short leg is here. But if it's up like this, then the short leg is down here and the long leg is up here. That's all you need. And that's it. And if you know the lengths of the legs of those triangles, you're good. You're set to go. So here we go. This is what pi over 6 looks like. It's the shallower one, right? It's not tipped up really high. It's like shallow, a little bit up like that. Okay? So that means that sine is the short leg, it's 1/2. Cosine is the long leg, it's √3/2. Done. That's it. That's it. Okay, let's do this one. Um, Geez, let me see here. Okay. I'll say this. I have a lot of these examples. So maybe I'll just go through them. If at any point you would like to pause and try another one on your own, go for it. But I want to get through them because there's other things we need to talk about. And I don't want this lecture to get too long. But cosine pi over 3, sine pi over 3. Okay, where is pi over 3? Imagine the unit circle. Pi over 3 is about there. Okay, so that's the long leg, that's √3/2. That's the short leg, that's 1/2. So cosine pi over 3 is 1/2. Sine of pi over 3 is √3/2. And we're done. That's it. Okay, same thing. There's the picture. All right. Ooh, 10 pi over 3. 10 pi over 3. So here's how I do this one. Let's see, 10 pi over 3, that's 10 thirds pi. What is that, 3 1/3 pi? Okay, let's do a unit circle. Here we go. 1 pi, 2 pi, 3 pi, and then 1/3 of a pi. So I'm going to be like down here, okay? Down there, something like that, right? Okay. This is the long leg. It's negative √3/2. This is the short leg. It's negative 1/2. I'm considering the signs based on the quadrant that I'm in. Because my point is going to be over here, both x and y are going to be negative, right? But I've already done it. I'm done at this point. So cosine of 10 pi over 3 is negative 1/2. Oops. And sine of 10 pi over 3 is negative √3/2. And we're done. That's it. So again, not memorizing a million angles. We're just memorizing those two triangles and understanding how to work with angles in a meaningful way. That's all it takes. That's really all it takes, right? There you go. Picture I just drew, and those are the results. So I encourage you to do that too. All right, now to finish things up, to answer that question about the nice angles, let's talk about some number theoretic results. One thing I want to say is remember that sine and cosine have a range of -1 to 1. So what that means is that these functions will hit every real number in that interval. The outputs will hit every real number in that interval. More precisely, if you pick any real number y in -1 to 1, then there is an angle such that sine of theta equals y. All right, there is an angle that will give you that number. However, for most nice angles, the values of sine and cosine are transcendental or they're at least irrational. So this is why I say that those angles that we are talking about are kind of like the only nice ones because most of the angles are going to be transcendental and most of those values are going to be transcendental. So in other words, the values of sine and cosine at the quadrantal angles or those shown in those special right triangles, they really are kind of the only nice values, all right? Otherwise, they're going to get kind of gross. Yeah, so there's some interesting theorems related to this idea that do deserve some attention. So I want to talk about them here now, just to illustrate what I'm talking about. One of them is called Niven's theorem. And check this out. So in the interval 0 to pi over 2, so in the first quadrant, if theta is a rational multiple of pi, and sine of theta is also rational, then theta must be one of those three numbers, 0, pi over 6, or pi over 2. Okay? So what we're saying is just looking in the first quadrant, because all the other ones are going to be similar, right? If you've got a rational multiple of pi, and the sine value at that angle is also rational, then there's only three possibilities for that angle: 0, pi over 6, or pi over 2. So what this is interesting because this is saying that virtually no angles that are rational multiples of pi will give you a rational output for the sine function. Yeah, so basically you're almost always going to get an irrational output. For example, pi over 7, that's 1/7 pi. That's a rational multiple of pi, and it's not equal to any of those. So that means that sine of pi over 7 must be an irrational number by Niven's theorem, this theorem up here. So that's what I'm saying. So maybe not the nicest angle, right? Then there's this theorem. So let's say that theta is a rational multiple of pi, like 2/3 pi, 27/64 pi. If it is a rational multiple of pi, then it turns out that sine of theta has to be an algebraic number. So that means if you've got a rational multiple of pi and you put it through the sine function, the result you're going to get must be an algebraic number. Remember, algebraic numbers are those numbers that are zeros of a polynomial with integer coefficients. That's kind of interesting. So, oh, also because this is true for sine, it's true for all the other trigonometric functions, the other five of them. So, yeah, this is actually kind of nice. One of the reasons that this is nice is because any angle given in degrees is a rational multiple of pi. Yeah, remember? 1 degree is pi over 180. Pi over 180, that's 180 times pi. That's a rational multiple of pi. So that means that anytime you evaluate a trig function given in degrees, the result is going to be an algebraic number guaranteed. Gonna guaranteed, right? But again, almost always going to be an irrational number. So it may be algebraic, but it's going to be irrational. So some examples, sine of 20 degrees, that's going to be an algebraic number. Cosine of negative 125 degrees, that's going to be an algebraic number. These aren't standard angles, right? 20 is not a standard angle. 125 is not a standard angle, right? So you're going to get an algebraic irrational number when you try to evaluate these functions. Tangent of 98 degrees, those are going to be algebraic numbers. Here's another example that I think you might appreciate. Sine of pi over 7 must be an algebraic number because pi over 7 is a rational multiple of pi. But if it's an algebraic number, that means there's a polynomial with integer coefficients where sine of pi over 7 gives you 0 when you plug it into that polynomial. And in fact, here it is. This is the polynomial that will do that. So P of x equals 64x cubed, I'm sorry, x to the sixth minus 112 x to the fourth plus 56x squared minus 7. If you plug in sine of pi over 7 to this polynomial, you'll get 0. That's it. So you can do this one on your own, but you can check it out in Mathematica using the full simplify command. Just do full simplify, compute that, and you will get 0. So the idea here is if you pair this theorem and coupled with Niven's theorem, you're going to get that rational multiples of pi will not generally produce a rational sine value. It'll be irrational, right? So not so nice, not so nice. And then there's this one. Okay, so this is kind of the big one. If theta is a non-zero algebraic number, then sine of theta is a transcendental number. Yeah. So what that means is, what that means is if your angle is an algebraic number, so relatively nice, then the output of sine at that angle will be transcendental, which is kind of wild. So this is basically taking nice numbers and mapping them to not nice numbers, transcendental numbers. And that'll end up being true for all of the other five trigonometric functions. This is actually why we emphasize those particular legs of those particular triangles and why we emphasize those standard angles, because they kind of exhaust all of the nice possibilities. And the other possibilities are not so nice. And in fact, you're pretty much always going to have to go to a computational resource to evaluate the trig functions at those non-standard angles. All right. Little note about this. This theorem is actually a corollary of a much more powerful theorem called the Lindemann-Weierstrass theorem. There he is again, right? Showing these things, showing up in all sorts of things. Yeah, again, this is what I just said. This is important because it asserts that even when your angle is relatively nice, like an algebraic number, the output of sine is going to be transcendental. A really good example, if you pick any rational number in radians, like 2, 3, 1/2, sine of theta will be transcendental. It'll be a transcendental number, not an algebraic number. So for example, sine of 1 is a transcendental number. So if you ever want to write down sine of 1, you might as well just stop right there. because any other result is going to be a decimal approximation. All right, that's it. Okay, on that note, it's time to play, okay? Thank you all again for watching this. I hope you enjoyed this. Remember to memorize those special right triangles, make sense of those standard angles, and they're going to help you all the way. They're going to help you all the way. Don't memorize a lot, memorize a little and use it to bridge all the gaps, okay? All right, I'll stop there. Thank you all again for watching, and I will see you next time when we talk about right triangle trigonometry. Have a good day.